So today we will see basically 4 things: a small intro on multimodal deep learning, then what is multimodal competition, the problem, and then 2 sets of solutions, some simpler ones and some more advanced. Okay, what do we know already? I will start with unimodal deep learning. We know that we have a lot of models that are very good on images, e.g. in our group, video, audio, on tasks, for example, as disease detection from chest x-rays, arrhythmias from ECGs, CT scans, ophthalmology, and several other tasks in any other domain. My favorite one is the goalkeeper one. We go from this point and we start discussing about multimodal. Each of these data can be considered one modality, but maybe we should define it a little bit better. So what is multimodal data? What is a modality, essentially? We refer to a modality as the way which information is expressed or perceived. And that can have different ways to represent it, from the simplest raw modalities, which are directly drawn from a sensor, an image, a signal, an EEG, whatever type of data you can measure from the real world directly, or then to more processed modalities where we put some structure into them, for example, language, or then detected objects in an image. And the fidelity that you give to that defines whether they're closer to the sensor or further away from it. But this is not all. To define a multimodal data case, we need the modalities to be heterogeneous and interconnected. That's something that we don't always know, but this is where it makes most sense to discuss about multimodal itself. Heterogeneous in the sense that the structure and the form of the data differs significantly. So less heterogeneous, homogeneous would be images from 2 cameras where they have exactly the same structure, or 2 signals. And as we go to more heterogeneous, it could be language and vision, EEG, and the demographic data, for example. And the more heterogeneous it is, the more challenging the task is. And then we have the interconnected data. Interconnected, we refer to these connections that the data have with between each other. So it can be some associations where they both share some information about a task, or it can be more intricate ones like dependencies or causality. And this is something that we're not aware necessarily from the beginning, but we can, if we are, we can take that into account. Sometimes we don't realize it, but the way that even us, our humans, process multiple modalities, it's quite surprising, because we think that we do some tasks based on X feedback, but sometimes we can be quite surprised. I have a small example which is extremely typical in multimodal presentations, where you are asked to find out whether the person that will appear says pa or fa.
Pa, 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 pa.
I don't know what you heard, but for most people, it's usually pa in the beginning and fa next in the second part of the video. And what we actually come to say is that the audio is exactly the same, and only the visual cue changes. And while we would expect this task to be performed only by our audio, I mean, we ask you, what do you listen to? But you are quite affected by the visual cue in that scenario. So even for humans, it's not very easy to understand how these things are processed, which modality do we focus more. And with multimodal, we can achieve several things. We can have many different tasks. Yeah. We can do we can go way beyond what's classically achieved. We can go from one modality to the other as image captioning or image generation from text to image, or we can combine both to achieve something better. For example, visual question answer. We ask a question, the answer is the label. Then in our group, we have a lot of sleep staging. We use EEG and EOG. In epilepsy, EEG, EMG, or personalized digital twins. We use the CT scan and the ECG. One example that I really like and I want to bring is this one, where we have one content image and the style description. And based on the style description, we need to change the style. I should move this to see properly. Okay, I want to focus on this last example where we have the two donkeys and the style description is apply cubism style to the left donkey in the image. And here, at least in the last one, which is the best version from the paper I got it, we can see that the model understands what is a donkey, what is the left, which one is the left donkey, what is the segmentation of it, what is the cubism, and manage to apply this style as well, which is quite impressive, I think, because it reveals how many more connections we can find and we can achieve with multimodality. Well, okay, some of these are based on the unimodal extraction of features of understanding, but they are revealed through this way. But for today, we will focus mainly on models that use more than one modality to achieve a task. And we will see that actually it's not that trivial to train such models, and there are problems that arise in that. And the problem that we will focus today is the multimodal competition. And straight away, I will go to what it is. We have observed ourselves as well, I will come to it, but also in previous papers that by using sometimes multiple modalities, we have a drop in performance. So here we have, in this paper, they used audio, RGB, and optical flow and different combinations of them. And then next to them, they have the best unimodal performance out of the modalities used there. And we see that in all cases, they had a drop, which is quite surprising because we give more information to a model and actually observe a performance drop. Similarly, they measured throughout the training in a different paper by using different fusion techniques or training strategies, and still the only one that managed to reach was the unimodal, to reach higher than the rest. In our case, we extend this one step further because achieving better than unimodal is the first goal, but it's not the only goal. We compare regarding to the ensemble of the unimodals, meaning that no further training is elaborated, but we take the unimodals and we combine them, we combine their predictions. And we do observe that while we train such a model, and now I've been to video audio action recognition is the task here. We see that the audio linear probing, which means that we take the latent space of the already trained and we train a classifier on top of that and we measure the performance. So no, there is no gradient from this loss going to the model. We see that the audio follows extremely closely the multimodal, and the video remains on chance level predictions throughout the whole training. And this creates a gap between what is already achieved by just using these unimodals, the same encoders trained unimodally, combined in an ensemble. And then we have this performance drop. We also notice, we measure the magnitude of the gradients while training unimodally and multimodally. With a dust line, we have the unimodal and the full line is the multimodal. And we observe that the audio line follows a bit more the unimodal. So the multimodal gradient magnitude follows a bit more throughout the training, the unimodal. While for vision modality, this decreases and goes approximately to 0, meaning that this modality is not getting enough gradients to be trained. I want to give some definitions, but I know this is a little bit too much of a text, but let me explain. These are the formal definitions given by the paper who put some structure into it, I would say. So basically what it says is that there is some probability that at least one or more modalities will dominate the training, meaning that these will be trained while the others, they will remain in correlation input-output similar to the beginning. So basically chance level. And we go one step further to notice two things. We attribute the multimodal competition to misdirected and vanishing gradients. And we define the multimodal competition error, which is just a lower bound on the generalization of the model. So the stronger the competition, the worse our model is going to perform on new data, on the generalization problem. Before we go to any solutions, I thought of stopping 1 second here in case someone has a question, because I think I already have explained more or less what is the problem, and now we will see how we can solve it. Shall I go on? Yes. Okay. We have two sets of solutions that I want to present. We will start with a few that have been proposed by literature, and we will group them as the simple. I will explain why, and then we will go to some more advanced. Okay, the first one says, okay, we assume that the problem is that at the end of a network, in this case, they use late fusion, which means that there's just a summation at the end, that the weights and the input, so that the final linear layer, somehow favors one of the two modalities more in the beginning. And if we manage to put the magnitude out, so normalize basically both the features here and the weights, then we will manage to give some gradients to both, and we will not have such a problem. The second work, I will go a little bit fast on them, but the second work says, okay, the problem is in the learning rate of each encoder. So what we will do is we will measure here, this is basically the cross entropy of each of the modalities. So SI means the cross entropy in I step of the training. So that's a small problem, I have to admit people. And they take this, basically, they measure the unimodal performance. So we have the prediction 1, prediction 2. And then we take the performance on step 5, and we compare with the previous steps. And we say, okay, if this decreased, we should change the learning rate accordingly and make it smaller such that our model manages to continue training and not overfit. That's the intuition. But here we see that each modality is compared separately. So we don't care about how the other modality is performing in that task. And that is the next idea, where they have the same score functions. Again, essentially, it's the cross entropy. Then they create a ratio among them, and they create these Ks where we change the coefficient that change the learning rate based on the ratio. And finally, the last work I want to show here is one that noticed that actually we do take the unimodal performance, but we don't train for unimodal performance. So we just assess it in these works as half of the last linear layer, which it does perform to some extent, but it can also be misleading. And the last work just added some losses. It's a little bit of too much for the equations, but basically they added some classifiers on top, and then they create this beta and gamma, which are now the coefficients that change the how much gradient it goes back to the classifier, to the encoders. One difference here is that they only balance the unimodal gradients and not the multimodal. So now we have presented a bit fast some algorithms that do approach this problem. And we can go and check if they're any helpful to this problem. And to our surprise, they actually perform worse. So what you see here is the performance drop, the performance difference compared to an ensemble. And we see that all methods, both, the unimodals, the joint training refers to a training of a model like that with a single joint objective. And then the others are the different cases, the different strategies. And we see that they all perform worse than just an ensemble, which was quite surprising for us. And we started thinking, an ensemble reaches X amount of accuracy. Can we do better? Is there any reason to train them jointly? And we assessed that by this very intricate plot. So in the x-axis, we have the true positives and false positives of the two unimodals. So it means that false or true means whether the model was able to find the correct answer or not. So we have both false means that both modalities were wrong in the prediction. And on y-axis, we have what the multimodal did, whether the multimodal found this prediction. And with that, we see that the circled ones are the cases that the unimodals are wrong on its own. And then when combined together, they manage to solve, to find the correct label for these data points. And in an ensemble, we already have some percentage of this. Here I'm using the two different models, Conformer and ResNet. And we see that by using the joint training that performs worse than the ensemble, we already managed to increase that number. This is averaged over some faults, so it's the difference is also significant. Which gets us to the point that doing multimodal training is not only about making a good routing system that leverages all points of the two models, but it's also managing to extract some more information about the data, which will hopefully lead into better classification and more data points. So information extraction. But we saw that current methods don't really give much. And we were facing the question of how can we improve it. And we did some steps. So this is a solution that we gave. So first, we added also the multitask losses. So unimodal classifiers on top of each representation, and then losses based on them. Here I have the gradients as well. So with blue, we have the audio gradient, and with red, the video. And then we created also such a balancing mechanism that gives more or less gradients based on them. The difference here is that we apply these estimates, these coefficients to both unimodal and multimodal gradient. This is a difference with the previous methods, while we allow both for acceleration and deceleration. So we can also increase the learning rate, something that was not used in the past. And the last one, when both modalities perform similar, we have a self-muting. We thought of it, and basically when they perform similar, then the method is muting itself. And with this, we did provide the first method that managed to surpass the previous, and by a very small margin, the ensemble. I will show it a little bit later, the comparison with the ensemble. And we used here multiple different data sets and fusion methods from linear, MLP, some fusion gates, film and gated, and then transformer as fusion. And let's see how we did compared to the synergy we were discussing. the synergy meaning the points that both modalities had false. We see that in some cases on the conformer, we did manage to increase that a little bit, while in the other case, we did increase it from joint training, but we didn't increase it much from previous methods. So previous methods performed a little bit better. I'm referring to this number here, the 6.3 compared to 5.7. The difference is small, but still we would like an algorithm that improves that as well. While we see that this method performs kind of a better routing, bringing similar error rates to the different modalities. So focusing on both, I would frame it. Something that we should note on, and on that we will start the discussion of have we solved this issue, is these data points that are in these categories. So the data points that at least one of the modality, the audio was true, the video was true, or both were true, but the multimodal failed. And it's those data points that we actually miss, and it's those data points that we could achieve. So the best routing strategy and the best multimodal algorithm essentially would find these points. And this is quite significant amount. It's around half of the data points in each case. So we see that we still have room for improvement. Yeah, so we're not done yet. We haven't solved this problem completely, but what did we miss? I will go a little bit theoretically to show something. So I'm going to mutual information. I know this is a little bit scary for a lot, but what I'm aiming to show is that basically we want to maximize this. We want to maximize the mutual information. So we want to maximize, or we want to get the most out of it, meaning that what is the capabilities that we have when using both x1 and x2 to predict y, compared to when we have only x1 to predict y and only x2 to predict y. So when we consider them together or separately. Because when we consider them separately, we can hypothetically achieve X amount, but this synergy that we saw before cannot be achieved. So this is where we should start from. And this gives us a small intuition on why previous works do not necessarily are as good as they could. Because they assume heavily through measuring unimodal performance to assess how good one modality is compared to the other. They assume on this independence. They assume that if my modality performs well on its own, it means that it also contributes significantly to the output, which is not necessarily true. If we put a well-trained modality there, it doesn't mean that it will give much to the output, especially if you have a complex model as fusion, then you are not sure about that at all. And this can be also misleading. But how can we fix it? So, okay, unimodal performance is not a good way to measure the contribution. What is it? How can we go there? And the answer would be some forms of explainability. And now Göran will take, no, I'm kidding, but Göran has helped me a lot in that. So the first way is supply values, and it's also one of the previous methods that we didn't elaborate before. So what do? They change one of the modalities at each time with 0 values, and they observe how much the output changed based on that. So if you have a bigger change with the zeros being on modality 1, it means that modality 1 is more important than the other. And very similarly, we do also with noise or permutations. So we add noise to one modality and we measure the difference of the output. If the difference is large, it means that this modality contributes more to these data points. So then we know that it does contribute and it's significant. We know its importance. And while 0 values and noisy can give us more local estimates, meaning that for each data point we can measure. With permutations, we can measure only for a bunch of data points. We cannot do it for one. Permutations meaning shuffling basically the data within a batch. And this is the way that we saw it, that we can improve it. The previous works have only focused on supply values for it, and there are some on the noisy. But there is a problem with the noisy, and that's what we come to save with the permutations. So when you want to add noisy estimates, you need to go to the input space, add some noise, and pass it again from your encoders. That is a problem because most of these encoders usually are quite large, and you don't have the opportunity to increase your batch by X number of samples, meaning X times your batch size. So permutations can happen in the latent space. As you see here, we go from Z1 to Z1 tilde. And that allows us for a cheap computation of such importance. And we use that. We have here the whole components of the solution, but I want to mainly focus on one of them. So basically, we estimate these permutations. We have these here, the combinations of one permuted modality, one non-permuted. We pass it, and we estimate the prediction based on having one of the two being permuted. And then we compare the y hat, the normal, with the y tilde 1 or 2, and we say, okay, this modality, having this modality permuted means that it doesn't have any connection with a label. It doesn't give you something for the label. It's almost, it's basically, you could add anything there from the whole data set. It will not give you any information on average, at least. And we estimate the difference. JSD refers to Jensen-Shannon divergence, which is a way to measure distance between probabilities. And we measure the difference basically between the probability estimate of having both your modalities and the probability estimate of having one of them perturbed. And this gives us a metric of how important this modality is. And ideally, we would like both of them to increase. We would like both of our modalities to have a high contribution, a high importance. And this could sum up with one more detail that some of the previous methods, also ours, we were considering whether we should equalize this contribution. But we realized fast that this is not the correct way to go, because in a task, maybe one modality offers more information and should contribute more. So it's not that we should perfectly align them, but more maximize them both. Well, now and we came to realize that the total importance is actually constant, in the sense that while both can contribute, if one contributes too much, it means that the other will contribute less. It will not allow for space. You can think of it as a debate between two, or a conversation. If one is shouting and making more noise and gives his opinion in a stronger way, it will not allow the other person to really express what he has to say. And having it constant turns this into a constant sum game, meaning that the two modalities compete to increase their contribution, and this can actually be formed into a game. So here we employed some game theory to achieve that, and we have three strategies. The first one is the collaborative. So we see that increasing the importance of modality 1 increases when we minimize the loss of MIPD. MIPD is the difference of modality 1. So here we have both modalities. So both modalities care about both MIPD1 and MIPD2, meaning that both modalities try to increase not only their own contribution, but also the other modality's contribution. In the second case, each modality cares only about itself. So maximizing only its own contribution. And in the third case, it's the greedy version, where it wants to increase its own contribution and minimize the others, so such that its own again increases further with the constant sum game. And all this gets us to some results. So this is the whole method. We have the permutations, and then we have the game strategy. And we go to this synthetic dataset example, where we want to test whether our decomposition of this mutual information that I mentioned before has any particular importance, and whether we are actually using testing on these cases. And here on the graph, we took different scenarios where in some of them we have all the information shared among the modalities, or then slowly decreasing the amount of shared information and leaving them not connected. So they have no data points that they share information about. And we see that with the black line, we have the single loss joint training. And we see that it decreases further its performance while the shared information decreases. While when it's not when there is none of shared information, then it manages to gain some back. And any of the previous methods also sometimes does improve it, but ours gives the best improvement on this. And then some results the way that we saw it before. So the accuracy difference compared to the ensemble. We provide the first algorithm that it's actually giving significant results, significant improvements over the ensemble. So the first one that does improve multimodal learning as a training strategy. Okay, so here we are, some key home messages. So what did we get from today? We found out that getting the most out of multimodal is actually difficult. We saw multimodal competition as an optimization problem, and we saw that the joint objective is not enough. We saw how it can be improved by adding multitask losses, and I didn't stress that out a lot, but also some pre-trained encoders. It was some part of it. And then we saw that measuring unimodal performance is not a good way to assess the contribution of each modality. And finally, we saw that multimodal competition can be actually formed as a game. So that's it. Thank you.